So a few years ago, before I started making podcasts for a living, I worked as the wholesale director for The Barn, a Berlin-based coffee roaster. And I remember I was on the phone with one of our cafe customers in Oslo because they had a problem. They were like, James, everyone's talking about water. Like, what type of water you use in coffee makes a difference. But is it worth us spending all this money on a water filtration kit? I don't think we should. Because, in Oslo, the water out of the tap tastes really good. And when it comes to water for coffee, I think a lot of people have this same assumption. If the water tastes good by itself, and then you add high quality coffee, you're going to get an even tastier beverage. And the opposite is true. If the water itself doesn't taste very good, and then you add coffee, then your coffee brew won't taste particularly good. But here's the thing. As far as my taste buds are concerned, that's not true. Because a few months ago, I actually put that assumption to the test. I hopped on a train from Berlin to the offices of BWT, Water and More. They're the sponsor of this episode, and they provide water filtration kits to cafes. And I hopped off the train in Wiesbaden, a small city along the Rhine in Western Germany. And at the BWT office, they had stacked a big rectangular table in one of their meeting rooms with cups, bowls, and kettles. We were about to taste some water. So this is how the test was going to roll. I would taste 4 different waters by themselves. And then I'd taste those same waters, but this time boiled up and added to coffee. Okay, so the first water I tasted was literally water out of the office kitchen tap. Local Wiesbaden tap water.
That's really good water. That's delicious.
And for the record, I would happily pay money for a bottle of that. And then I tried that same Wiesbaden water that had come straight out of the tap, but it had been filtered using one of BWT's Best Max Premium water filtration kits.
Yeah, it kind of tastes a bit metallic. There's a kind of a sheeny coatingness to it. It's kind of a bit odd.
This filtered water by itself, it didn't taste bad, but it had nothing on Wiesbaden tap water. Now, using the logic of that Oslo cafe, right? Delicious water plus delicious coffee equals even more delicious beverage. The unfiltered, straight out of the tap Wiesbaden water should be the one that tastes the best with coffee. So I ground out some coffee, which, by the way, was a Yogurchef roasted by Nano Cafe here in Berlin. Added the hot water to the ground coffee in bowls. And I tasted regular Wiesbaden tap water plus coffee.
Flat. Not very interesting. Not particularly acidic.
And this water, which tastes amazing by itself, you add it to coffee, and the coffee tastes kind of lame. And then I tasted the coffee made with the BWT Best Max Premium filtered water, which I didn't initially like because it was sheeny, metallic. But you add that to coffee.
Ooh, I like that. I like that one.
It was as if I turned the key on a perfume box, and as it opens, you get a waft of jasmine.
I like number 3. 3 is great.
And so, thinking back to that cafe that I consulted all those years ago, that cafe would have tasted this and they would have realized it doesn't matter what water tastes like by itself. It matters what's in it and how that interacts with the coffee. So it really begs the question, what kind of water makes the best coffee? And to answer this question, I want to take you first on a very long journey. I want to go right back to the formation of the earth and tell you the story of how minerals and even water itself made its way into our dear earth. And I'm doing it this way because water science is extremely complicated, and it's also something you're going to forget. Everybody who's not a chemist tells me this. But with a great story, you might remember it just that little bit longer. So after taking you back to the formation of the earth, I'm going to show you how minerals get into our water and why certain minerals are often to blame for your lame tasting coffee. And I should be clear, lame to someone like me, and maybe you too, someone who likes acidity, vibrancy in their coffees. And then I'm going to show you why this same story about how minerals get into our water to make my coffees lame, this same story also compromises your kettle and espresso machine boiler. And that's just the first half. Because in the second half, I want to tell you the story about how the specialty coffee industry tried to figure out what does make good water for coffee by sharing the story of a rather famous book and the big impact it had, but also the reaction from the more established scientific community and how that led to what we have today as the Specialty Coffee Association's Water Quality Handbook. And at the very end, we're going to explore the sponsor for this episode, BWT, one of their commercial filtration kits and how they work. And if you're not a coffee professional, you just love to make coffees in your kitchen, I'll explain how you can get water which will make your coffees taste more vibrant. Assuming, of course, vibrancy is what you're looking for. I'm James Harper, and this is The Science of Coffee, a spin-off series from my coffee documentary podcast, Filter Stories, and a journey into coffee's hidden microscopic secrets. So to kick us off on this very, very long story, I spoke with a very respected author.
I'm Marcia Bjornerud. I'm professor of geosciences at Lawrence University in Appleton, Wisconsin in the US.
Marcia wrote the book Timefulness, How Thinking Like a Geologist Can Help Save the World, Geopedia, a brief compendium of geologic curiosities, and a book that my dad, when he read it, he honestly wouldn't shut up about it for like the next 5 years, which is Reading the Rocks, the autobiography of Earth. So how can geology help us make sense of water for coffee? Well, this story is going to explain why maybe your coffee tastes a bit boring, and also why perhaps your kettle looks like someone dumped a bag of flour into it. So let's go back billions and billions and billions of years ago, before there was an Earth. Where did all the stuff that makes up what's on planet Earth come from?
So all of the elements that make up our solar system and the Earth itself are recycled in some sense. They're from earlier star systems that finally ended their lives in spectacular explosions, and the stuff got remixed and incorporated into new stars and solar systems.
And now let's go to our little corner of the universe. Because here, at one point, billions upon billions of years ago, a star blew up in a spectacular supernova. All the pieces that will eventually become you, me, all those pieces are fired out in all directions. And slowly, gravity pulls them back in. Dear Mother Earth literally falls into place.
And we think that this actually did happen relatively quickly, geologically speaking, between that supernova precursor star that blew itself up and gave us the guts that became the planets, and the time that the core of the Earth separated was probably only about 30 million years.
So at this point, the Earth is a swirling mess. Now the really heavy elements, like iron, they are sinking down into the middle of the Earth, creating, our molten core. But where did water come from?
So that's an interesting thing. We don't even know where all this water came from. Earth's abundant water is really kind of a mystery. So there are two possible sources. It could either be primordial, so that would be primordial water that has been here since the beginning, or, and these aren't really mutually exclusive, it could be a combination, it could be that much of the water was imported after the planet formed from comets.
But however it happens, there is a lot of water. Now, if I were a Martian coming down and taking a look around, my first thought would be, this is an aquatic planet, because most of the surface of the Earth is covered in water. But that is not even the half of it.
So there's about probably like 3 oceans worth of water in the Earth's mantle that is delivered there through the process of subduction, where ocean crust, after it gets cold and dense enough, sinks back down into the mantle in places like Indonesia or the coast of South America, where coffee is grown. And that ocean crust carries huge amounts of water locked into the rocks and puts water back into the mantle, where it will eventually reemerge through volcanism in this very long-term, like 100 million year timescale.
Hold on. There is already a ridiculous quantity of water on the Earth. Are you saying there's 3 times that just sitting underneath the surface?
Yeah, in the mantle of the Earth. Some people think up to 5 oceans worth of water.
That's mind-blowing.
It is.
Water. There's a lot of it. And of course, without water, you haven't got coffee. But this is now where I want to go one layer deeper, because it really matters what is in the water in terms of the minerals, as to A, how it's going to affect your kettle, and also how it's going to make your coffee taste. And so what I want to do here is introduce a character, a protagonist, calcium. Now, if you Google calcium and you see it like all clumped up together as like pure raw calcium, it is actually a metal. It's like a shiny metallic, almost a bit like graphite. So yeah, have that in your mind. A little microscopic piece of shininess. So, the world, 4.6 billion years ago. It is
the very start of geologic time, called the Hadean, which essentially means the hellish time or the hidden time.
I think oftentimes when we think of the formation of a planet, we think of a lot of lava everywhere, hellish. But let's imagine this little shiny piece of calcium. And the thing about calcium is that it melts really easily. And so in this, what we think is a very hot environment, the calcium melts.
So there's kind of a distillation process that happens when the mantle partially melts. Those elements that are more easily melted out have gotten concentrated in the crust. And one of those is calcium.
And so in the early formation of Earth, it's a swirling mess. Heavy metals are floating down towards the core, like iron. But calcium, which is relatively light, I mean, not as light as the things that make up water, hydrogen and oxygen, but light relative to iron, it's probably melted and floats up towards the surface of Earth and gets deposited in the crust, right literally under our feet. And then, of course, on the Earth, we have a lot of water. We don't know quite how. It evaporates. We have rain. The rain comes down to Earth. It hits the ground. And as the water slowly makes its way to the sea, the water slides its way across calcium deposits.
So over time, inexorably, water dismantles crystals, picks them apart into their constituent elements, carries those in solution, usually to the sea.
So in the early years of the Earth, the sea is a soup of many minerals, one of which is calcium, possibly in combination with other things like calcium hydroxide. And so while all this is going on, rains, calcium being taken to the sea in different forms, something else is also happening at the same time. Kind of important to the story of coffee. That little thing known as life.
The earliest, probably unambiguous evidence of life is at about 3.5 billion.
And we think the Earth is about 4.5 billion years old.
So 1 billion years into the history of the planet, we see the first fossilized microbial features called stromatolites.
Now, during my conversation with Marsha, I found this piece particularly interesting.
I'm a vegetarian and I look kind of fondly back at that long ago time.
There is a point in Earth's history where it is a vegetarian paradise.
So there's this moment in the evolutionary past we call the Cambrian explosion, which after 3 billion years of essentially microbial life on Earth, we start to see evidence of macroscopic life forms and animals.
So the first life on Earth are very, very simple, microscopic life forms. And over time, they get quite busy evolving and eventually start photosynthesizing. And so at one point, the ocean is full of these tiny little microscopic photosynthesizing organisms. Think algae and, other very simple organisms. But, evolution is a process that continues. And these critters become more and more complex, bigger, macroscopic. You can actually see them with your eye.
And the first animals were just soft-bodied things, worms and things that didn't have any body armor.
And for a brief period in evolutionary history, we were in the vegetarian paradise.
And this sort of seems to be this Edenic time when most of these organisms were just grazing on the seafloor and picking up detritus where they could find it. They weren't eating each other.
They weren't eating each other. It only lasts a couple of dozen million years. But while it lasts, it's glorious. Critters around the world, all living peacefully side by side, not afraid of one another. But around 500 million years ago, one day, little critter thinks, I'm sick of eating this muck that's floating around. These other critters look pretty nutritious. And voila, the death of the vegetarian paradise and the birth of predation. Predators. So now you have little critters eating other little critters. And this bit's key in the story of Water for Coffee, because
it was predation that caused the invention of shells.
The little critters which are sick of being eaten start developing protective armor.
Shells become important because if you're soft, squishy, wormy kind of thing, you're going to get munched.
Now, I absolutely guarantee you have seen these shells, or the remains of them, when brewing a cup of coffee. So, a primary ingredient in these shells is calcium, a little microscopic glittering protagonist.
The shell is made of both calcium and the carbonate part, which in the ocean is technically bicarbonate. And those things combine and form the mineral calcite, which is what the shell is made of. So the creatures are taking both the calcium ion from igneous rocks and dissolved carbon dioxide that's in the form of this carbonate and making the calcite.
So these critters that don't want to get eaten, they're taking the calcium and combining it with another thing that's kind of floating around in the ocean, which is bicarbonate HCO3. And all that really is carbon dioxide, which is in the atmosphere, which has been dissolved into the water in the sea, because, fun fact, water dissolves CO2. And in this chemical soup of water, there's also hydrogen floating around, and they all come together to form HCO3, bicarbonate HCO3. That combines with our shiny little calcium protagonist to create the shells that these critters use to protect themselves. So our protagonist here, calcium, it's got to another stage in its, journey of existence. It is now calcium carbonate. Now, what does that look like?
I live on dry land, but this area was once below sea level and a warm, shallow, tropical marine environment in which different calcifying organisms were living, dying, and essentially ending up in limestone.
So what happens is that for millions upon millions of years, these little critters, they're making these shells. And when they die, they float down to the seabed. The squidgy bits of these critters, they decompose and kind of move away. And what's left is their hard calcium carbonate shells. And over so many years, that is what creates limestone.
The White Cliffs of Dover are the classic example. If you look at that white, chalky limestone under even a pretty low magnification microscope, you see it's just fossil shells that have accumulated over time.
Now, I've actually never seen images of limestone under a microscope, so I'm going to Google it now. Oh my God. This is wild. It is a patchwork of different shells, a million little small shells all packed on top of each other. And each one of these, we know that each one of these was a critter. Wow. Okay, so now let's start connecting some dots. Why does your kettle look like you dumped a bag of flour into it, and your coffee, without you maybe even realizing it, tastes a bit flatter duller than it could. So let's look at now how water comes out of your tap. Now, quick caveat, what I'm about to tell you doesn't apply to all the water that comes out of all the taps across the world, but I would argue there's a more than 50% chance that this is how it actually works with water coming out of your tap in your kitchen. So, if you were to open your tap right now, that water at some point in the past fell from the sky. And as it fell, it transformed a little bit, became acidic. And to explain further is Summer Smirkay, a researcher, academic chemist at the Coffee Excellence Center at the University of Applied Sciences in Zurich.
This rainwater, it picks up carbon dioxide in the air, and then the raindrops are very small, so they do very quickly pick up the gases from the atmosphere, and water becomes slightly acidic. And therefore, rainwater is typically slightly acidic.
So this kind of blew me away when I first learned about it, but H2O, water, reacts with carbon dioxide that's in the air, CO2, and it forms a type of acid, carbonic acid. Now, for clarity, this is not the same as acid rain, separate thing. But water,
it can also pick up other acids from the pollution in the air. So basically, if we have air that is polluted with nitrous oxides or sulfur oxides, and there's a rainfall around this polluted air, the raindrops will be very quickly acidified by the air.
And so if you live in a place with dirty air, that rainwater is going to be even more acidic than just the mild acidity when it interacts with the CO2 in the air to produce carbonic acid. So this slightly acidic rain, or very acidic rain, if you live in a place with polluted air, hits the ground and starts to seep underground. It nudges its way deep between rocks, and the thing is, bedrock made of limestone is extremely common. And as we've heard, limestone is the protective shells of those ancient little critters. And so this now slightly acidic water begins to dissolve the limestone. Now, limestone has another more technical name, calcium carbonate.
Calcium carbonate is not soluble in pure water. It's very slightly soluble. However, if we add a slight amount of acid into the water, it can dissolve in water. Therefore, rainwater with slightly acidic pH dissolves calcium carbonate, and so the carbonates get into our water. And when this water goes underground, we have groundwater which has a certain level of carbonates in, and also calcium, magnesium, among other salts.
So this now slightly acidic water hits this calcium carbonate, this limestone, the remains of the shells of those ancient critters, and begins to dissolve them. And they create bicarbonate. Bicarbonate. Just like, bicarbonate of soda that you can buy in your supermarket. And if you are a keen listener, you would have noticed Samu mentioned, as water is picking up calcium carbonate, it's also picking up magnesium.
We have groundwater which has a certain level of carbonates in, and also calcium, magnesium, among other salts.
Now, magnesium is super important in the story of water for coffee, and we'll come on to it later. Just know that it's at this point where rainwater is trickling its way down rocks under our feet that magnesium is incorporated into water. Now listen, I've teased this long enough. I'm tying this now to coffee. This process of slightly acidic rainwater reacting with limestone creates two things we need to be aware of when it comes to coffee. One has to do with espresso machines and how to keep an espresso machine boiler from gunking up, and the other has to do with the flavor of coffee. Let's touch on the flavor first. The water that has seeped down underground through the limestone bedrock and is coming out of your tap, that water has bicarbonate in it. And here's the thing about bicarbonate. It increases the water's buffering capacity.
Buffering capacity means how strong one solution is able to neutralize a base or an acid. So if water has strong buffering capacities, it means that it will neutralize the acids in our coffee. So it will lower the acidity of the brew.
So to explain buffering capacity, let's imagine water with absolutely zero buffering capacity, which would be water with no bicarbonates in it, pure H2O. Its pH is absolutely neutral, neither alkaline, neither acidic. Okay, let's say you brew a cup of coffee with that water, right? So water hits the coffee particles, and the water begins to extract flavors from those coffee particles. Now, coffee itself is full of many, many, many compounds. And one thing it has is organic acids, like, for example, citric acid. So citric acid could be pulled into the water from the ground coffee. And so now the water, which was previously absolutely neutral, becomes acidic. And an acidic solution is by definition one which has a pH less than 7. And if a solution has a pH above 7, it's basic. And here's the thing about pH. It is the measure of the concentration of hydrogen ions in a solution. And a simplistic way of understanding this is it's like the number of protons that are moving around somewhat freely in a solution, tagging onto one molecule over here, free floating, tagging onto another molecule over there.
One of the definitions is as an acid is a molecule that can donate a proton. So when we talk about acidity, it's this exchange of protons in a solution. And when something is eager to accept it and something is ready to deliver it, it just happens in water. No, it happens in an incredibly short amount of time.
Right, so we have water, and we have now an organic acid in the water. There are many acids in the water which have protons. They are donating protons to the water, exchanging protons amongst themselves. And while all this madness and cacophony is going on, at one point, we pick up the cup of coffee and we take a sip. And the organic acids hit the receptors on our tongues.
It reacts with our receptors, donates the proton in the receptor, and we feel this as our sensory response of acidity.
So if water has 0 buffering capacity, there are many acids which have protons. And when those acids hit our tongues, protons are donated. And that donation of a proton to the receptor on our tongue, that is our sensation of acidity. But let's talk about buffering capacity. Because if you were to add in some bicarbonate, you know, the bicarbonate from the limestone and the ancient shells of our ancestors, and you want to make some coffee with that water, which has some bicarbonate in it.
The citric acid donates this proton to the hydrogen carbonate, and therefore it's not a citric acid anymore because it doesn't have this proton that an acid by definition needs to have to be an acid.
So water hits the ground coffee. It pulls that little piece of citric acid out of the coffee into the water. The proton in the acid is pulled out of it, as in the citric acid donates its proton to the bicarbonate in the water, and boom, neutralized. The acidity just disappears. There's a very quick momentary change in the acidity of the solution, but it gets back to where it was. And when we take a sip of that coffee and the citric acid hits our tongue, because it's missing a proton, we do not get that sense of acidity. And it doesn't stop there. A little bit more citric acid is extracted into the water and boom. Again, that organic acid donates its proton, loses it, and the brew doesn't turn acidic. This water has a high buffering capacity. And if you look at water comparison charts, you will see the term alkalinity, which is the measure of the strength of a buffering solution. So alkalinity is just another way of saying the strength of the buffering capacity of water, how good it is at neutralizing acids. But let me just zoom out for a second, because what this means is that the dissolved limestone in the water, which has come from the shells of those ancient critters, has made it harder for you to taste acids in your cup of coffee. And so if you live in a place which has a lot of limestone, if you brew a coffee using that tap water, your filter brews are going to taste flatter, like less acidic than they could be. So that's the flavor side. A lot of dead critters under your feet, less acidity in your coffee. Now, here's the other really interesting thing. These little critters, making our coffees taste a bit lamer than they could, that's not all they're ruining when it comes to our kitchens and making coffee. They also ruin our kettles and espresso machine boilers. Because if you live in an area with a lot of limestone, when you heat up the water, a chemical reaction takes place.
In high temperature conditions, this hydrogen carbonate will break down into carbonate, and therefore will have this precipitate of insoluble calcium carbonate. So kind of going back to where it was originally as calcium carbonate, but where we don't want it.
So if we were to zoom into that very limestone heavy water that you have just put to boil in your kettle, the calcium carbonate that came from the shells of those ancient critters is in the water. But because of the heat and a few reactions, the material that made those ancient shells reforms in your kettle. And it produces that wonderful white substance that so many of us are familiar with, limescale.
Well, yes, the first one here, the very hard one, you can see it's almost white and milky.
And I saw this for myself when I was at the offices of BWT in Wiesbaden. They had some transparent kettles, which they were boiling very hard water in. And I could see calcium carbonate, you know, the same material that those shells were made of, reforming before my very eyes. Wow, yeah, look at that. So on the bottom of this kettle, one boiling, you can already see there's like a very, very fine silt. Wow, that's wild, from one boiling session. Now, Professor Marsha, our geologist, she lives in a very limestone-heavy area, as do I, and maybe you do too. And this is the crazy thing about brewing a cup of coffee. The act of boiling a kettle, which has a lot of calcium carbonate in the water, we are participating in something that's a bit, kumbaya, circle of life, the cycle of samsara.
These rocks, as rocks do, they have many reincarnations, are now being redissolved and their constituents released into the water. And our water here is notoriously hard. It builds up as lime scum in showers and in our coffee makers. And so that's recycled calcium. It's primordial. It's been with us since the formation of the earth. It probably came to the crust through volcanism. And who knows how many times it's been cycled through different rocks and organisms to end up in my cup of coffee. Many times.
All right. Enough of that. Let's move on now. So why does the reformation of calcium carbonate on our kettles, why does it matter so much, if you're a coffee drinker? Well, if you are the proud owner of an espresso machine, your boiler could be experiencing a lot of this limescale buildup. If you live in an area with a lot of limestone in the bedrock, I'm looking at you, London, Berlin, San Antonio, Tampa. Just imagine, I saw limescale formation from the boiling of one kettle once. And the boiler in an espresso machine, the thing that heats up the water, it's like a closed off kettle. All this limescale buildup is literally hidden in a closed off cylinder. Now, I was really curious to know, how bad can this get? And when I was in Wiesbaden at the offices of BWT, I spoke with their general manager.
My name is Frank Neuhausen. I'm working for BWT Water and More since about 17 years. And our absolutely focus is the coffee business.
Now, before Frank joined BWT, he was actually working in academia as a scientist. But since joining BWT, the organization has actually sold over 1 million commercial water filtration kits around the world. And specifically for people who live in an area with very hard water, I asked Frank, what would happen if you filled your espresso machine boiler with water straight out of the tap?
You can really see boilers, let's say, full of scale, or even leaking tubes because of corrosions and so on.
What does it cost to replace or to clean out, descale a boiler?
If you need a service technician that does it descaling, it will take some hours that you have to pay. And in some cases, even some tubes or valves or boilers might be more or less destroyed. So they have to exchange them.
This sounds to me like $2,000.
Might come up to this, yeah.
Okay, so we know that too much calcium carbonate is bad for an espresso machine boiler. Solution? Simple. Let's just get rid of all the calcium carbonate in the water, and we're gravy. And that is the absolutely wrong message to take away from this. The thing is, not enough calcium carbonate is also a problem. Water can be corrosive, especially at higher temperatures, and when it has very few minerals in it at all. And part of this comes back to the whole concept of buffering capacity that we explored earlier. Water which has a low buffering capacity, basically water which gets acidic very easily, all the hydrogen ions which are present in the water, as in all the protons, as in the fact that this solution, this water, is quite acidic, react with the metals that make up espresso machine boilers and remove electrons from the metal, and in doing so, corrode the metal. But somewhere in between a lot of calcium carbonate and not very much calcium carbonate is the sweet spot for water. The place where a metal boiler won't be corroded, but it also won't be gunked up with limescale. And that, about 10 years ago, was the state of understanding in the coffee industry when it comes to water for coffee. Not too much, not too few, somewhere in the middle. So now I want to tell you a different story. A story which tries to answer the question, what are the optimal mineral concentrations in water to produce a really good cup of coffee? For someone like me, of course, who loves acidity.
Before we get too deep into this, let me have like one sip of coffee.
So let me introduce to you a professor of chemistry I spoke to.
My name is Professor Christopher Hendon. I am a professor of chemistry at the University of Oregon.
So 10 odd years ago, Christopher was a budding young chemist, and he was doing his PhD at the University of Bath in the UK. While working on his PhD, he stumbles across, the beauty, the delicious world of specialty coffee. When he tasted
a coffee that tasted so unusual, and at the time it was just a naturally processed coffee, but I'd never had something like that before.
And so he frequents this cafe more and more often, and the cafe is Colonna & Smalls, run by Maxwell Colonna Dashwood. And it's here where his world of computational chemistry collided with the specialty coffee industry.
Basically what happened was Maxwell used to be a multi-roaster cafe, and that involved him buying beans from all over the place. And I think the story goes that Colonna & Smalls purchased a coffee from Square Mile,
a London-based coffee roastery co-founded by James Hoffman, the now YouTube celebrity.
And there was a disagreement about whether that coffee was defective or not. And in essence, Maxwell tried to dial this thing in and was arriving at flavors that he perceived as negative. So coffee went back to James, and James cupped it back in London and arrived at it being perfectly fine. They're good tasters. They definitely are not disagreeable people. And so when there's a difference in opinion that's so dramatic, there must have been some other scientific basis for that. And so we began to look at what possibly could have happened and arrived, obviously, at water chemistry differences.
And so Maxwell got busy trying to understand water science himself. And at one point, he asked one of his regulars, Christopher Hendon, a chemistry question.
Yeah, so his original question was, what does TDS mean, and how can it tell us about quality of coffee? And I immediately responded with something along the lines of, it means nothing. And I have no idea why this ever evolved to be a metric that people would use.
Okay, now here's the thing. At the time, the coffee industry's understanding of what good water is for coffee essentially boiled down, no pun intended, to TDS. TDS is total dissolved solids, and in the context of water, it's really just the measure of the amount of minerals, metals, organic minerals, and salts that are dissolved in a certain volume of water. And that could be anything that's not water itself. Calcium carbonate, magnesium, other salts, you name it, could all be in there, measured by this thing, TDS. Now, to be clear here, we're not talking about the TDS of coffee. You don't use a refractometer, which you might be more familiar with. You use titration kits, or you stick a probe in there to measure the conductivity. Anyway, the point is, it was the TDS of water that was being communicated by one of specialty coffee's largest trade groups at the time.
So the idea originally in the coffee world was that water had to have a TDS of less than 135, or at 135, right? And they'd broken it down a little bit more, plus and minus in some areas, but the point was 135 was the number. And the reason that they gave was because anything above that was risky to your machine, and anything below that was risky to your machine.
Now, in some ways, this is very intuitive. We explored this in the first half of the episode. Too much calcium carbonate in your water? Your kettle, your espresso machine boiler gungs up with limescale. Too little? You're going to corrode your boiler, corrode your kettle. But to someone in professional academia like Christopher Hendon, TDS, it was an overly simplistic measure because looking at just the amount of total dissolved solids in the water, looking at just that number, it doesn't tell you what specific minerals you need in the water to give you a good cup of coffee. It also doesn't tell you what the buffering capacity is of the water. And of course, buffering capacity is very important in specialty coffee because we quite like acidity. Now, Christopher himself didn't have the answer as to what specific minerals you should put in your water to get great coffee. But he and Maxwell decided to write a book, Water for Coffee, that tried to help the coffee community understand the science of water better.
So what we started with in the book was a discussion of where atoms come from and understanding the process of creating atoms, which you can then use to build molecules, which you can then understand function of molecule once you've got a collection of them together in a liquid.
The book was essentially an undergraduate water chemistry textbook for coffee people.
But we were trying to teach people more than water. We were trying to teach them scientific process and reasoning.
And it was such a novel concept at the time that they bootstrapped the publishing of it.
Yeah, we self-published the book because we felt as though we were talking about a scientific topic that people did not have a resource at the time.
Now, the book made a huge splash, again, forgive the pun, in the specialty coffee community, and they sold a fair number of books too.
Well over 10,000.
But of course, it's not just specialty coffee people who are reading this book. Other academic chemists who had a strong interest in coffee also got hold of the book. For example, it landed on the desk of Professor Shahan Yeretzian at the University of Applied Sciences in Zurich.
I'm Shahan Yeretzian. I'm here professor in the Institute of Chemistry and Biotechnology. I'm heading two groups. One is analytical technology, and the other is what we call the Coffee Excellence Center, which is a center focusing on the science of coffee.
Okay, so a book came out a few years ago by Christopher Hendon. When you read it, what were your thoughts?
Well, that's essentially where we decide to go into that subject, because when we read it, we realized that there were some major scientific errors that would be misleading the whole community.
Now, the reason Shahan is quite critical of the book is because Christopher's approach and the way he presented his recommendations for Water for Coffee are quite different from how a more conventional academic chemist would approach the topic. I don't want to go into the deep details of this. It's really a case of like a lot of small critiques building up into a larger critique. And to give you like one tiny example, when discussing like a good mineral concentration in water, Christopher used milligrams per liter.
So we recommended an upper limit of something like 70 milligrams per liter of bicarbonate as the ion floating around.
And here's the thing, in chemistry, you could express the amount of bicarbonate in water using lots of different measures. One is weight, milligrams per liter, which is what Christopher used. You could also use moles, which is like the number of them. But Christopher used weight because
it was to teach people that water starts out with nothing in it. And you can go ahead and weigh out stuff, and then you can taste the difference yourself. That's on you to figure out what you like, but you're going to do it by weighing it.
But to more conventional chemists, such as Shahan, he didn't think milligrams per liter was the appropriate unit.
It's not linked to the reality of what the coffee community needs.
And why would it be problematic if we used milligrams?
It's absolutely correct. You can measure the weight of magnesium and calcium, but it doesn't help you to develop a story that goes into application.
And so other chemists have explained to me that if Christopher had used a different measure, for example, if he had chosen to use moles, which is the number of bicarbonate floating around in the water as opposed to the weight, then water compositions could be more accurately defined and it'd be more easy to compare waters in different cities and their respective mineral compositions. But despite all of that, the academic chemists in Zurich did start a dialogue with Christopher, raised their concerns, and in some cases, he does agree with the feedback.
He was right in saying that if we still go by mass, we can't decouple calcium and magnesium, which is true, and we have fixed that.
And Christopher told me that he's planning to incorporate these changes in a new edition of the book that he's currently working on. And during my conversation with Christopher, when we took a step back and reflected on the impact of his book, Water for Coffee, the way he sees it, it contributed to what has become a total sea change in the world of coffee science.
Because what it resulted in was the beginning of the SCA directly investing in science.
SCA, the industry's major trade group, the Specialty Coffee Association.
So even if it was inflammatory, and even if I didn't make friends initially, those people that I didn't make friends with initially are now very close friends.
So what did the coffee trade bodies actually do after the publication of Christopher Hendon's book? For Frank Neuhausen at BWT, who around this time became a part of the Specialty Coffee Association,
I also joined the SCA in the board of directors, and I think it's a fantastic organization really providing huge benefits to the coffee community.
the publication of Christopher's book was personally a wake-up call for him.
This was, let's say, one of the starting points of getting deeper and deeper in all the discussions about water for coffee. And what we also did in parallel is we worked together with the University of Zurich and prepared, I think it was in 2015, the first booklet on water for coffee.
So essentially, BWT, a water filtration manufacturer, partnered with the Coffee Excellence Center at the Zurich University of Applied Sciences, headed up by Chahani Retzin, who we heard earlier, and together created the Specialty Coffee Association's Water Quality Handbook. The approach of the book was very different to Christopher Hendon's. They didn't try to teach the fundamentals of water chemistry. It was a much more practical manual.
And we developed the concept of measure, aim, and treat.
Measure the minerals in your water. Aim towards where you would like the mineral composition to be. And treat. Apply appropriate filtration to get you there. And they also established what might be a good range for the mineral composition in your water.
A zone that ensures both a very good extraction and avoiding corrosion and avoiding limescale.
Now, what you need to know is that the mineral recommendations in the Specialty Coffee Association's Water Quality Handbook are expressed as the sum of both magnesium carbonate and calcium carbonate. And we explored this earlier. There's a good chance that the calcium in your water came from those ancient shells of our ancestors, and when it rains, slightly acidic water picks it up as it slings its way through the rocks under our feet, and while it's picking up some calcium, it's also picking up magnesium. And here's the thing, in the world of coffee, it really matters how much magnesium there is in your water. For example, after the publication of the Specialty Coffee Association's Water Quality Handbook, Frank Neuhausen at BWT partnered again with the University of Applied Sciences in Zurich to study how magnesium affects coffee's flavor.
And the outcome, more or less, is that the typical flavor of a coffee that is, let's say, desired or the target of a roaster,
a specialty coffee roaster,
more or less easily can be achieved if you have a high ratio of magnesium versus calcium.
For the specialty coffee lover's palate, magnesium in your water makes your coffee taste more vibrant.
And the outcome was that there is a clear, strong, remarkable difference in the taste and also in the chemical composition of the coffee.
And this research was published in a white paper, which I've linked in the show notes. So, if you're like me, while I was putting this story together, I would go to my kitchen, open my tap, pour some of Berlin's finest, hard, calcium carbonate-laden water into my kettle, and brew a fine cup of coffee. But I knew it could be a lot better. Because the water's buffering capacity was so high, all those acids I was pulling from my specialty coffees were disappearing over and over again. My coffees weren't tasting as vibrant as they possibly could. I wanted to fix this. I wanted a more vibrant cup of coffee. And so I want to finish this episode on ways that you can get more vibrant coffees. First up, we'll look at what the professionals can do, and then what you can do in the confines of your own kitchen. Okay, so you're a cafe. Well, first up, depending on where you live, you may not even need to treat your water that much. Read the Specialty Coffee Association's Water Quality Handbook, link in the show notes. But let's assume you live in a hard water area. I want to show you BWT, the sponsor for this episode, their latest water filtration kit for cafes. So I see there are two tubes here, two canisters. It looks like a giant double version of a soda stream.
Yeah, you're right. It looks a little bit like that.
So this giant double soda stream looking thing is the BWT Best Aqua ROC. And at a high level, it's very easy to understand. So let's pretend that you are a droplet of Berlin tap water. You're very hard, full of calcium carbonate. You flow into the first of the two canisters, which is a reverse osmosis system, RO for short.
What an RO system does is it reduces, in general, the total content of all minerals given in the water.
If you were to slice open this first canister, you would see rings and rings and rings of a membrane,
where only water particles can go through, and ions as calcium and so on cannot pass this membrane.
So an RO system, in short, basically strips out a whole load of minerals from your water. And BWT have a smartphone app where you can actually measure how much is being taken out. But the amount of minerals in the water is still a bit problematic.
But this quantity will not ensure always that you do not get problems in the coffee machine due to limescale buildup and so on. Therefore, we have a second step.
The second step is the second canister. So the water, which has had a lot of the minerals stripped out of it, now flows into this second canister, which swaps out some of the remaining minerals for magnesium.
It's an ion exchange technology where we take out calcium ions still in the permeate and exchange versus magnesium ions.
And so now the end water has a relatively high proportion of magnesium and the level of calcium carbonate, which you need to not corrode your machine and also not to gunk it up full of limescale. But also, importantly, you can choose to add in a relatively high ratio of magnesium to calcium carbonate if you want your coffees to taste even more vibrant. If you want to learn more, I'll put a link to the website in the show notes.
And by our website, you also can get in contact with our local people. So local people can teach you all about it, because in our understanding, it's always the best to talk to each other and get it explained on site.
Okay, that's the commercial side. But what about us poor home users? We don't need these systems that are designed to pump out hundreds of liters of purified water every day. Now, the good news is that there are many solutions, but I only recommend maybe one or two. First up, here are all the things I don't recommend. Are you a geek, a science nerd? I mean, if you're listening to this, maybe you are. So go online, buy some titration kits where you can measure the hardness and the alkalinity of your water. Or if you want to save the hassle, go to the website of your water supplier and look at the mineral composition of your water there. And then you can cross-reference that with the Specialty Coffee Association's Water Quality Handbook. And you could then do what a commercial operator could do: measure, aim, and then treat. Problem is, first of all, you have to wrap your head around the Water Quality Handbook. It takes a bit of time. And then you need to find a filtration solution that gets you from where you are currently in your water composition to where you want to go. And frankly, I'd be surprised if you could find a filtration kit that works for your specific setup for less than a couple $100. But I really can't stress this enough. Beware the complexity you're going to get yourself into, which is why I don't recommend this. Another option, which I really don't recommend, find a brand of bottled water in your local supermarket which has a good mineral composition. But plastic waste, the CO2 footprint. Another option is to buy pure distilled water, like lab-grade water, with no minerals at all, and then you could add the minerals in. There are kits online you can purchase for this, but again, the trouble is that you're dealing with bottled water, and making distilled water takes a lot of energy in the first place, which results in a relatively high CO2 footprint. So for me, personally, that's why I wouldn't do it. So here are my two actual recommendations. Number one, if you are somebody who doesn't mind a rather awkward conversation, you could just trundle on down to your local cafe when they're not too busy, and you could politely ask them to fill up a 10-liter container with their filtered water. But I'd feel really awkward having that conversation. You also might want to tip them quite generously for the help. Purifying water costs money. And what I actually use in my own kitchen now is cartridges. And specifically, when I visited BWT in Wiesbaden, they gave me one of their Penguin water filters. You know what these look like. Big plastic jug, cartridge in the middle of it. But what I like about it is that it takes out calcium. Great. A lot of water filters already do that, so it makes the water less hard. But while taking out the calcium, it swaps in magnesium. And if you live in a hard water area, you might want to consider this sort of solution. But if you live in a soft water area, you don't see very much limescale buildup in your kettle, chances are your water is going to be pretty good. Okay, maybe it's going to lack a bit of magnesium. That's all right, because at least the buffering capacity will be quite low, so your brew should be relatively vibrant anyway. But if you're really hellbent on increasing the magnesium content in your water, you can add in some magnesium sulfate. Plenty of options online. I've also put a how-to in the show notes. Be careful, don't add too much. And also, very important, don't add pure magnesium to water because it's going to explode. It's magnesium carbonate or magnesium sulfate. And with any luck, your brews should now be exploding in new flavors. So thank you for listening to my first episode on coffee science. The next episode drops in 2 weeks, but if you want to hear the next 2 episodes right now, head to my new podcast channel, The Science of Coffee. Link in the show notes. This series has been the most ambitious thing I've ever tried to make. And if you liked what you heard, one thing that keeps me really motivated to make these sorts of complicated stories is to see, people taking the time to listen to it. And so please share the episode with your friends. Share it with your barista, the local cafe owner you might be on good terms with. Not that many people have heard of Filter Stories, and I really kind of rely on people like you to spread the word. And if you're new to Filter Stories, you probably are wondering, who is this James Harper? And I think this is a good opportunity to kind of just introduce myself again if you don't know who I am. So I'm Italian-Australian, and I began my career in London in finance. And, after a few years, I realized that everybody was dead behind the ice. So in 2013, I decided to quit that and tried to find a new path and decided coffee. I'd always loved it, as a drink. Cafes were these really special spaces. And I was also attracted to the fact that specialty was trying to avoid doing the very exploitative things that big commercial coffee was doing. So in 2015, I jumped into it. I worked in wholesale for big roasters, for small roasters. I also volunteered to help stage manage the barista championships in different countries. But after a couple of years, I kind of hit a ceiling. I was dying to understand how things in coffee really work. And in particular, who are these farmers? And why are they growing coffee for us? And are they really getting a good deal like so many roasters tell us? And alongside my passion for coffee is my passion for audio storytelling. I've been listening to narrative shows like This American Life for almost a decade. So in 2017, I did as much research as I could. I bought some microphones, a one-way ticket to Guatemala, learned Spanish in 6 weeks, and launched what became Filter Stories, my main documentary podcast. And ever since then, I've been trying to help other organizations across the industry make good podcasts. For example, I work on Allegra's Fifth Wave podcast, the Specialty Coffee Association as well. I made a podcast series for Bellwether Coffee. And even outside of coffee, I've worked with organizations such as Duolingo and Porsche. And what keeps me in podcasting is I love the fact that podcasts are free. And I think they're a really powerful medium to help the specialty coffee industry progress further and for coffee lovers to just learn about coffee. And if you want to follow my journey from now on and see all the things I get up to, you can follow me on Instagram at Filter Stories Podcast. Link in the show notes. Now, for this episode, I really want to thank Christopher Hendon, Marsha Bjorn-Ruden, Frank Neuhausen, and the team at BWT for letting me invade their offices for a day, Samuel Smerke, and Shahan Yeretzian. And also, by the way, if you want to go deeper into the science of coffee, the Zurich University of Applied Sciences has an online course, which I've linked in the show notes. Now, let me tell you what's coming up in the rest of the series. So the next episode is going to be on the science of coffee extraction, because there are many different ways you can brew your coffee, and they all change how it tastes. And I share a story in the second half about how Macro Beverage Systems SP9 Brewer was basically developed to remove many of the variables that affect extraction. Then, after that, we're talking genetics and the sustainability crisis that coffee growers are facing. Water, very important for brewing coffee, also extremely important for growing coffee. And I take you with me on a trip I took with Traboka, our green bean supplier, as we visit Kenyan coffee farmers to show you how they're managing the recent drought. And then, in the 4th episode, I'm going to show you how espresso machine technology has changed these last 150 years and has culminated in fully automatic espresso machines like those made by Eversys. And you know, in this episode on water, I showed you how espresso machine boilers can be a very expensive mess for a coffee shop owner. But let me tell you, that sort of problem is nothing compared to the problems espresso machines had historically. The penultimate episode will be on the science of milk foam. And here's a fun fact. So in this episode, we learned about the buffering capacity of water and how, if your water has a high buffering capacity, that's not great, of course, if you like vibrant coffees. But when Oatly were developing their Barista Edition oat drink, they had a problem that it kept splitting when you added acidic coffee to it. And so what they did is increase the buffering capacity of the Oatly. And then in the final episode, I'm going to show you the research and development landscape in coffee more generally. And for example, take you into the factory of Firenzato to show you how they developed their all-ground grinder, which allows the home barista to grind coffee fine enough for espresso, but also coarse enough for filter. And this entire time, we've explored how water can change the flavor of coffee. But I have to say, it is probably most noticeable if you're drinking a filter rather than an espresso. Now, I want to thank Peter Giuliano and Britta Fulmer for editorially consulting me on this series, and to Raymond Detweiler for helping me wrap my head around the complexity of water chemistry. Sound and editing assistance was provided by Cole DeCharco. This series was produced by me, James Harper, and I also write and play the piano music. And until next time, take care and brew great coffee.